This is the first in our series of lectures on section 1.5, entitled Basic Proof Methods 2. Here we're going to talk about the overall structure of proofs by contraposition and contradiction. Okay, so this is the sort of proposition we're going to be trying to prove using the method of contraposition. Let me make a few comments about this. So this is the sort of thing that we said quite a bit about in the previous section. And I always like to write things in symbols, and the reason that I like to write them in symbols is that it suggests to me how I should respond to it. And how I respond to something like this depends upon what it is I'm interested in doing with it. If I'm merely interested in stating what it says, I would say, for every x in U, if P of x, then Q of x. But on the other hand, if I'm interested in giving a direct proof of it, I wouldn't say that. I would say, let x be an element of U, suppose P of x is true, and then ultimately I would try to deduce from that that I could prove that Q of x is true as a consequence of P of x being true. Now, we know that any conditional statement has the same truth value as its contrapositive, and therefore proving if P of x then Q of x is the same as proving if not Q of x then not P of x. And so the method of proof by contraposition is just simply a direct proof of this same statement where we replace this by the contrapositive. And therefore the overall structure of the proof by contraposition should look like the following. Okay, so here's the basic format of proof by contraposition. Looking at this, I say, let x be an element of U. And then in the next sentence, I warn the reader that I'm about to give something other than a direct proof. And so I say, we argue using the method of contraposition. This is really an optional sentence. It makes it a little bit clearer for the reader, but you don't have to do that, as long as you do everything else correctly. Okay, so now we're going to give a direct proof of the contrapositive of this, which is not Q implies not P. And so we say, suppose that Q of x is false. Then we have a sequence of logical steps, and we say, therefore P of x is false. So as usual, of course, this therefore P of x is false comes by giving a sequence of logical steps. And so we're trying to deduce that P of x is false as a consequence of Q of x being false. Note also that you shouldn't take this stuff completely literally. You know, let x be an element of U isn't exactly the way it has to be written. For example, if this was for all x in R, you wouldn't say let x be an element of the set of real numbers, because that's a little awkward. You would say let x be a real number. And this, suppose that Q of x is false, what you would really write is you would really write the assumption that a certain useful denial of Q of x is true. So write it out in a way that's useful for what you're about to do. Well, at this point, that's really all I have to say about it. We're going to do examples in future videos. Let's now turn to the structure of a proof by contradiction. Proof by contradiction is a lot more flexible than the proof by contraposition, because you can apply the method to the proof of any proposition, whereas you can only apply the method of proof by contraposition to a conditional statement. So the idea of the method is that any statement has exactly the opposite truth value of its negation. And so if you can prove that the negation is false, then the original statement must be true. And so in the proof by contradiction, what you do is you begin by assuming that the negation is true. You prove that that leads to a contradiction, and therefore the original statement must be true. Okay, so let's apply that method to something that looks like this, and let's begin by writing down what the negation of it is. as a useful denial. So that comes out to the following. Okay, so the negation of the original statement is what? We change this to a there exists, and we negate this. There exists an x in u such that not a of x. So the method of proof by contradiction is you say, suppose that this useful denial is true, and you show that that leads to a contradiction, and that means that this negation cannot be true, and therefore the original proposition must be true. Okay, so the overall format would look something like the following. Okay, so here's how a typical proof by contradiction would work for a statement of this form. So we start by warning the reader that we're going to use the method of contradiction. And so it's really a good idea, because otherwise the reader could be very confused by how you're continuing. So we say we argue using the method of contradiction, and now we're basically supposing that this happens. So we write, suppose that there exists an x in u such that a of x is false. Well, then you have a certain sequence of logical steps leading to the ability to say that you've reached a contradiction. In other words, you've come to a step that can't possibly be true. So the moment you get to that, you have the right to say, thus the original statement is true. Now let's apply the method of proof by contradiction of a statement that looks like this, of a conditional statement that's universally quantified. So let's recall what is the useful denial of a statement of this form. It is that there exists an x in u such that, then a useful denial of this is not conditional at all. It's p of x and not q of x. And so a useful denial of this is there exists an x in u such that p of x and not q of x. So let's now, for this particular type of proof, let's write down proof by contradiction. Okay, so this is what it should look like. We argue by contradiction, and now we're going to suppose that this happens. So we say, suppose there exists an x in u such that p of x is true and q of x is false. You then have a sequence of logical steps. You arrive at a contradiction, and so you say, this is a contradiction, thus the original statement is true. So that's a proof by contradiction for a universally quantified statement that is a conditional. Okay, in the next sequence of videos, we're going to look at several examples of these things.